In this presentation, I'm going to explain previous gate questions and answers, and the topic is power, electronics and drives, and this is the part 1. Now let us see the problem. First problem, problem 1. Thyristor T in the figure below is typically off and it is triggered with a single pulse width of 10 milliseconds. This circuit. It is given that the value of inductance is given by 100 by pi microhenries and capacitance C is equal to 100 by pi microfarad. Assuming the latching and holding currents of the thyristors are both 0 and the initial charge on the capacitor is 0, T conducts for how much duration this thyristor conducts? That's the question. And the answers are given here. And now let us analyze the circuit. That is, when this circuit or when the SCR is on, that is when the thyristor is triggered, it gets turned on and the circuit becomes, that is this circuit will become whatever this shown below. Therefore it is circuit becomes 15 volts applied to an LC circuit. Therefore this is simply an LC circuit to which 15 volt is applied. That is 15 volt is applied to an LC circuit. Now, in order to find out the duration for which the SCR is conducting, we have to analyze this LC circuit. And LC circuit, to analyze that one, we are first applying the Kirchhoff's voltage law to this loop. That is, input voltage is equal to, that is Vs, we are taken as Vs, which is equal to the drop across the inductance L di by dt plus what is across the capacitor 1 by C integral I dt, which is equal to Vs, that is given as 15 volts. And if you take the Laplace transform to solve that, finally I want to find out what is the current through this LC circuit, or that's also called ringing circuit. And in order to find out that one, we are first taking the Laplace transform of this equation, or in that case L into SIS minus initial value of the current in plus 1 by C IS divided by S plus initial value of the charge Q0 divided by S. That is equal to, if you take the Laplace transform of the constant Vs, which is equal to Vs divided by S. Again, we are finding out what is grouping to that one. I0 and Q0 is given 0. Then this equation become, that is IS into SL plus 1 by CS equal to Vs by S. Therefore, this is the equation to be solved, or you have to find out what is the current by taking the inverse Laplace transform of this one. And here IS can be taken as Vs by S into plus 1 by S square plus 1 by LC. Therefore, now we have to find out the inverse Laplace transform of the IS, so that we'll be getting what is the current through this LC circuit. Now, if you take the inverse Laplace transform, of course, here, if you take this one, 1 by LC is defined as the resonant frequency, which is omega, which is equal to omega naught, it is called omega naught equal to 1 by root of LC. That's called the resonant frequency. And if it is omega naught, this one, I can write it as this part I can write it as omega. I'm converting this one S square plus omega square. Now I'm multiplying numerator and denominator by omega naught, where omega naught equal 1 by root of LC. Therefore, the omega naught divided by S square plus omega naught square. Then of course here Vs by L into omega naught, because I have to multiply in the numerator already multiplied, therefore you have to denominator also have to multiply. So that this equation now here, omega naught divided by S square plus omega naught square, if you take the inverse Laplace transform, it is nothing but sine omega naught t. And here if you apply here V0 divided by L into omega naught, which is equal to 1 by root of LC, that becomes V, that is whatever that one, sorry, Vs into root of C by L. Therefore, if you take the inverse Laplace transform, this current, it becomes Vs into root of C by L sine omega naught t, where omega naught equal to 1 by root of LC, which is called the resonant frequency. Now, if you take the corresponding voltage also, we can get what is the capacitor voltage can be calculated, which is equal to 1 by C integral I dt, or that is equal to, it is equal to Vs into 1 minus cos omega naught. Anyway, omega naught is called the resonant frequency 1 by root of LC. Now to find out the duration of this one, this is the current waveform as such, we can say that because this obeying this equation, and this is the voltage across the capacitor obeying this equation. Now we have to find out what is this duration for which the thyristor will be conducting, and that is nothing but which is equal to pi by omega naught. Pi by omega naught, that will be finding out in the next slide. Now continuation of the previous problem here, we have to find out this duration for which the thyristor will be conducting. So for pi by omega naught, for pi by omega naught you have to calculate for your omega naught equal to 1 by root of LC, and you are calculating 1 by root of LC. You are substituting for the value of L 100 divided by pi and C 100 divided by pi, and into of course microfarad and microhenry, it is into 10 raised to minus 12, and then we'll be substituting, we'll be get 10 raised to 4 pi is the resonant frequency omega naught. Then substituting this equation, pi by that will be getting, it is equal to, that will be getting 100 microseconds. Therefore 100 microsecond is the duration for which this thyristor will be conducting, and therefore the answer is, it is equal to, the option is C is the answer. So now let us see another problem, that is problem 2, which is purely, it is a drive based problem in which the separately excited DC motor that is shown in the figure has a rated armature current of 20 amperes and a rated armature voltage of 150 volts. And ideal chopper switching frequency, that is the chopper switching frequency is 5 kilohertz, is to control the armature voltage, that is the voltage across this one. And if the armature value of the inductance equal to 0.1 millihenry and armature resistance equal to 1 ohm, neglecting the armature reaction, the duty ratio of the chopper to obtain 50% of the rated torque, and at the rated speed and the rated field current, 50% of rated torque, what should be the duty ratio of this chopper? That is the question, and the answers are given. In order to do this one, now let us see that one. Rated armature current is given as 20 amperes, and the rated armature voltage is given as, for this machine, it is equal to 150 volts, and inductance value 0.1 millihenry and armature resistance equal to 1 ohm. And now, as you know that one, torque is proportional to phi into Ia. For a DC motor, torque is proportional to phi into Ia. For example, if it is phi is rated value, then it's a constant one. It is T is proportional to the Ia. Therefore, if 50% of rated torque means the current is also 50%. Therefore, let us see first at the rated value what is the back EMF. Therefore, at the rated speed and rated flux, what is the back EMF? Back EMF is nothing but the armature voltage minus I rated into Ra, or V minus IaRa. Therefore, 150 minus 20 is the rated current into Ra equal to 1, or equal to 130 volt is the back EMF at the rated condition, at the rated voltage, rated speed and rated flux. Now that is the back EMF. Now as half the rated torque means the current was, rated current is given as 20 amperes. Half the rated current means rated torque means the current will become 10 amperes. Therefore, here 50% of torque, the current will become 10 amperes. Now, corresponding to 10 amperes, you have to find out, because here the speed is not changing as well as field flux is not changing. Therefore, the back EMF is not changing. Since the back EMF is not changing, now we have to calculate what should be the voltage across the armature corresponding to the second case. In order to calculate the voltage across the armature, the required voltage to be applied, which is given by E plus IaRa. The voltage to be applied equal to back EMF plus IaRa. Back EMF, there's no change. Therefore, same thing 130 plus, but current has dropped to 10 amperes. Therefore, 10 into 1, it will become 140 volts. Therefore, the required voltage at the armature is equal to 140 volts, and the input voltage equal to say 150 volts. Input voltage, let us see that one. No, not 150 volt. Input voltage to the chopper is 200. This is equal to 200 volts. The rated of motor is equal to 150, but the input voltage to the chopper equal to 200 volts. And what the output across the voltage across the armature required we calculated as, it is equal to 140 volts. Therefore, the duty ratio is as you, this is a duty ratio is given by output voltage divided by the input voltage. Therefore, output voltage equal to 140. Input voltage equal to 200. Therefore, you will be getting 0.7 or 70% is the duty ratio. Therefore, the answer is 0.7, which is equal to the option D is the answer. Now, let us see the another problem. Basically, it is that, let's say that's common to the question number 3 and 4. The statement is that this is a boost converter actually, or you can say that chopper that feeds the resistive load, that is step up chopper like. Therefore, this is driving a resistive load from the battery, and MOSFET Q from the battery and the MOSFET switched at a 250 kilohertz. This MOSFET is switched at 250 kilohertz, and the duty ratio of this equal to 0.4. Duty ratio is nothing but on period divided by the total time period. For the all elements of the circuits are to be ideal. The question is that what is the feed surge resistive load? The question is the peak to peak source current at the ripple in the ampere. What is the peak to peak current at the source side? This what is the peak current source side? Of course. Now let us see that one. The two cases when the switch is on, here can say that when switch is on, this voltage is coming across the inductance, and so that the voltage across the inductance same as the whatever the supply voltage is marked as Vs, same as 12 volts, and that one. And when switch is off here, that is when switch is off, the circuit is like this one. Then output voltage equal to V0, and input voltage equal to say Vd, or the voltage across this one is given by Vd minus V0 or Vd minus V0. Or anyway, if you have a positive voltage across the inductor, the rate of change of current through the inductor will be having a positive slope. Therefore, the current is building up with a positive slope, and when switch is off, the current, since the voltage across the inductor is negative, the current is dying out. Therefore, this is the voltage across the inductor, and this is the current through the inductor. Now, the question is that what is the peak to peak source current? Therefore, current through the inductor is same as the source current at the source side. Therefore, what is the peak current? What is the peak current? That is the question. Therefore, in order to find out, input voltage equal to 12 volts and inductance equal to 100 microhenries. Now, the rate at which the voltage is building up, because VL equal to L di by dt, or di by dt is given by VL by L, or whatever the voltage applied here, but VL is nothing but the input voltage Vd. For Vd divided by L is the rate at which the current is building up, which is equal to 12 divided by 100 into 10 raised to, of course, minus 6, or that is the rate at which the current is building up, and that can be written as, once that is reaching to that, VL by D will become, it is equal to the peak value of the current divided by the on period. From within the on period, that reaches to the peak value of the current, that is this peak value. Therefore, if you know the on period, you can calculate VL by L into the on period will give the peak, peak to peak value. That is whatever this current change can be calculated. So the peak to peak source current is equal to I peak equal to Vd by L into on period. To calculate the on period, duty ratio is given as 0.4. Duty ratio is given by on period divided by the time period Ts. Therefore, Ts switching frequency is given as 250 kilohertz. Therefore, Ts is given by 1 by 250. Therefore, Ts equal to 1 by 250, or on period is given by the duty ratio 0.4 into Ts, or you will be getting it is equal to 1.6 microseconds. Therefore, the on period, the on period is given by 1.6 microsecond, and of course, input voltage equal to 12. Inductance is also given 100 microhenry. Then you can calculate within this time how much is the change in inductor current. That is given by Vd by L into T on, or 12 divided by 100 into 10 raised to minus 6 into 1.6 into 10 raised to minus 6, or it will equal to 0.192 amperes. Therefore, the current ripple at the source side, that is change in current, that is equal to 0.192 amperes. Therefore, the answer is C. C is the answer. Now, this is the extension of the same problem in which the same circuit as such. The question is that the average source current in amperes in steady state. What is the average value of the source current? Average value of the source current. As we have already seen that one, when switch is on, the voltage across the inductor equal to Vd. When switch is off, the voltage across the inductor equal to Vd minus V0. V0 is the average output voltage. Vd is the input voltage. Therefore, the current through the inductor is building up like this one, and this is decaying. Therefore, this is the voltage across the inductor, and this is the current through the inductor. The question is that what is the average value of the source current? It is nothing but average value of the inductor current. Therefore, average value of the output voltage is given by, this is actually a boost topology, boost converter topology, in which output voltage and average value of output voltage and input voltage, that is related by V0 by Vd equal to 1 by 1 minus T, or output voltage equal to average output voltage equal to 1 by 1 minus T into Vd. Or D is given, V is already we calculated, or it's given actually. In the previous problem, it is given, the same problem, 0.4 is the duty ratio. For V 1 by 1 minus 0.4 into 12 or 20 volt is the average output voltage. Now, once you get the average output voltage, that divided by the resistance will give the average output current. For average output current equal to 1 ampere. The average output voltage average output current, which is equal to 1 ampere, divided by the input current, average input current or source current or inductor current, that is given as I0 divided by Is equal to 1 by 1 minus t. That is the relation in a boost converter or boost topology. The output current divided by the input current equal to 1 minus t. Output voltage divided by input voltage equal to 1 by 1 minus t. Therefore, 1 minus d equal to, can calculate what is the source current. Average source current is given by I0 divided by 1 minus d. Average output current divided by 1 minus duty ratio, or 1 by 1 minus 0.4, which is equal to 5 by 3. Therefore, the average source current Is is given by 5 by 3. Therefore, the answer is 5 by 3 is the B. Answer B is the correct option. Answer is option B. Now let us see the problem 5. That is statement is actually statement for linked questions. Question number 5 and 6. This is a statement. The voltage source inverter VSI shown in the figure, same here, shown below, is switched to provide a 50 hertz square wave output. A 50 hertz square wave is generated, that is switched like this one. Output voltage and V0 across the RL load. That is the across the RL load we are getting a switch voltage. And reference polarity of the V0 and reference current directions are inputs are indicated in the figure. That is current, this reference current is like the same thing here, positive, and this is the positive current, and this is the positive voltage that is indicated. And it is given that resistance R equal to 3 ohms and inductance equal to 9.55 millihenry. The question is that in the interval when V0 average output voltage V0 is less than 0, that is negative, and output current is positive, more than 0, the pair of the device which conducts the load current, let us see that one, voltage is negative and current is positive. Therefore, these are the different regions as such, but same circuit is shown here. Here it is marked as S1, S2, S3, S4, and this is a positive voltage and this is a negative voltage, and this is the corresponding current that depends upon the load what we are connecting. It is a in RL load, therefore the current direction is like that one. The question is that when voltage is negative, that is during this period, voltage is negative as well as current is positive. Current is positive means this duration. This duration means voltage is negative and current is positive, means that these two devices are to be conducted, or here D1, D3 and D4 are to be conducted. Therefore, D3 and D4, that is here when D3 and D4 are conducting, here you can say that one D3 is conducting. Here the current is same as that one, positive current. Again, that is to D3, the current flow is like that one. But since this is connected to the negative terminal, here the voltage will become negative. For to get a negative voltage and a positive current, that is this duration, the devices that are to be conducted is equal to, of course, D3 and D4. That is D3 and D4. And therefore, in that one, the option is that D3 and D4. This is a D3 and D4. The devices which are to be conducting. Therefore, in a voltage source inverter, as you know that one, voltage polarity will be plus or minus. That depends upon the switching of this switches. If S1 and S2 are switching, we'll get a positive voltage, or S3 and S4 is negative voltage. But the current direction is decided by, the current polarity is decided by the whatever the load you are connecting. For this is the current polarity as such. And in that case, since you requires a negative voltage and a positive current, the devices are conducting during this duration is equal to D3 and of course D3 and D4. Therefore, the current direction is like this one, and you'll be getting a negative voltage. For the answer is, the option is D, D3 and D4. Now let us see another problem, connecting to the same problem, another problem 6, which is equal to appropriate transition, that is zero voltage switching or ZVS, or zero current switching of the IGBT during the turn on and turn off. That is during the IGBT turn on and turn off. That is first, what is the, whether it is zero voltage switching during off period, zero voltage switching during on period, or zero current switching during turn off period, or zero current switching during the on period. That's a question. Now let us see that one. For analyzing this again, H-bridge circuit here, when Q3 and Q4 are switched on, that is when Q3 and Q4 are switched on here, initially due to the reverse current that is flowing, that is because of an inductive load here, before switching on Q3 and Q4, there will be a, of course, there can be a current through having like this one, through D3, that is there will be of state, and the current passes through the diodes. In this condition, the voltage across Q3 and Q4 are zero as diode conducts. That is, before switching on this corresponding Q3 and Q4, because of the inductive nature of the load, there will be a current in this direction, which is it will conducting D3 and D4 will be conducting. Since D3 and D4 are conducting here, the voltage across the switch will become zero. That is why it is a zero voltage switching is possible because of this diode. Therefore, since the diodes are conducting, the conduction of this current through the passing through the diode, in this conduction, the voltage across the Q3 and Q4 are zero as the diode conducts. Hence, it shows a zero voltage switching during the on period. That during on period of the switch, since the diode is conducting previously, the voltage across the switch is zero. That's called zero voltage switching is during the on period is possible. That is why zero voltage switching, that is option B is correct. Zero voltage switching during the turn on process. Therefore, option B is correct. Let us see another problem. 7. A half controlled single phase bridge rectifier is supplying a RL load. It is operated at a firing angle alpha and the load is continuous, and the fraction of the cycle that freewheels diode conduct is, that is the duration for which it is freewheeling is taking place, that is to be calculated. Therefore, that is, in this case, this is the input voltage, and when T1 and D1 are conducting, you will be getting a positive like this one. The path is like this one. Therefore, you will be getting a plus here and minus here. That is here. And here, since we are using a diode in this one, that will be getting turned off. The device will be turned off. That is, diode is getting turned off. And when next pi plus alpha, the T3 and D2, or T3 is in here T1 and T2. T2 is getting turned on, and T2 and D2 are conducting. When T2 and D2 are conducting, here negative half cycle, here again the current is in this direction. Here are we getting again plus. Therefore, this is the output voltage. Therefore, this is the output voltage of this single phase half controlled bridge circuit. And in this case, the duration for which this freewheeling action is taking place, that is, when from 0 to pi, the devices which are conducting is equal to T2 and D1 are conducting. T2 and D1 that's called a freewheeling action is taking place. And again from pi to pi plus alpha, T1 and D2 are conducting. T1 and D2 are conducting. That's a freewheeling action. The question is that how much duration, that is, what is the fraction of the cycle that freewheels the diode out of the pi radians 180 degree freewheeling action take place T1 D1 or T2 D2 conduction, and that is alpha. This is the alpha duration. Therefore, so the fraction of the cycle of the freewheeling diode conducts is given by, out of the pi radians here, after alpha duration is conducting. Therefore, alpha pi is the duration for which the diode is freewheeling to this one. The diode and corresponding SCRs are conducting. Therefore, alpha pi duration. Therefore, this is answer is D is the answer. So, 8th problem is it's a direct question, simple one. The typical ratio of the latching current to the halting current of a thyristor. Latching current is the, of course, if the current above, forward current is above the latching current, that even absence of the gating signal, that continues to conduction. The minimum that current required, that is called the latching current. And holding current is that once it is conducting, if you are reducing the forward current below a certain value of current, that is called the holding current. Therefore, the ratio, what is the ratio? For a 20 ampere thyristor, what is the ratio of latching current to the holding current? Therefore, the latching current is always higher than the holding current. Usually, the latching current is taken as 2 to 3 times the holding current. That is a normal method. In this case, in this option, therefore, the best option is the B option. Answer B is the best option here. Now, let us see a problem 9. In this one, the circuit shown is an ideal switch as operated at 100 kilohertz. Therefore, this is actually a buck converter circuit in which the switch is operated at 100 kilohertz, and the duty ratio is equal to 50%. Therefore, on period divided by total time period, duty ratio is equal to 50%. Given delta IC, the change in ripple current in the capacitor equal to 1.6 ampere, and peak to peak 1.6 peak to peak, and the load current, average load current is equal to 5 amperes. This current equal to 5 amperes. And the question is that peak value of the current in the switch. What is the peak value of the current through the switch? Now let us see this is a, as I told you, this is a buck converter. Input voltage equal to 24 and the duty ratio is equal to 50%. Now here, now when the switch is on, as you know that when switch is on, the voltage across the inductor in a buck converter, the voltage is inductor is given by what is the input voltage minus the average output voltage. VD minus V0 is the voltage across the inductor. Since the voltage across the inductor is positive, the current through the inductor is having a positive slope. The current inductor is building up like this one, from certain value to another value. It is current is building up, and during that period the current is flowing through the switch because switch is on here. And when switch is off, through the freewheeling, there will be a current through the freewheeling diode or freewheeling diode, and in that case the voltage across the inductor is given by minus V0. Since the voltage across the inductor is minus V0, L di by dt equal to negative, the current is decaying like this one. Therefore, this is the current through the inductor, and once it is off, here the current through the switch will become 0. Therefore, there will become 0 again and switch is. Therefore, this is the current through the switch, and this is the current through the inductor, and of course, this is the current through the diode. The question is that what is the peak value of the current through the switch? Peak value of the current is this one. This is the peak value of the current. Now we have to find out that one. For that one, the peak value of the current is given by what is the average value of the current. This is the average value of the inductor current, same as the average value of the load current. Because average value of the current through the capacitor equal to 0, because current second balance based on that one. This average current equal to 0. Therefore, average value of the current through the inductor is same as the average load current. Therefore, this is same as the average load current, which is the average inductor current. Therefore, that average inductor current plus delta IL by 2. What is this? This is the delta IL. That divided by 2 is the peak current. Therefore, IL is the average value. IL is the average value of the inductor current, which is equal to same as the average value of the load current, because average value of the capacitor current equals 0. Because as the current second balance, the average current second balance to be the average current through the inductor, the capacitor equals 0. For the average current through the inductor, same as the average load current. Therefore, here the average value of the capacitor current equals 0, or delta. Now delta IL is same as the change in current, because here, since we are assuming a constant output current, the change in capacitor current is same as the change in inductor current, or delta IL is same as delta IC, that is given as the problem 1.6 amperes. Therefore, the peak value of the current through the switch is given by the average load current. The average peak current through the switch is given by IL equal to, given by IL plus delta IL divided by 2, which is average current, it is equal to I0, average load current, that plus delta IL by 2. Then average load current is given as, it is equal to, it is calculated as average load current is given by 5 amperes. Therefore, 5 amperes plus delta IL by 2, 1.6 by 2, or it is equal to 5.8 amperes. 5.8 amperes. Therefore, answer is C is the answer. Now let us see problem 10, in which in a three-phase inverter circuit shown, the load is balanced and the gating scheme is 180-degree conduction mode, and all the switching devices are ideal. Therefore, this is a 180-degree mode of conducting inverter, and here of course that is given to a motor setup, and the RMS value of the load voltage. What is the RMS value of the load voltage here? Therefore, here the corresponding phase voltage for a 180-degree conduction, these are the plot of the phase voltage. That is when there are the voltage is changing. Here you can see that one, the phase voltage is changing from here Vs by 3, and from 0 to 60 to say 120 plus 2Vs by 3. Again this is equal to plus 2Vs by 3. Here plus Vs by 3 from of course 120 to 180. From 180 to say 240, it is equal to minus Vs by 3. From 240 to say 300, it is equal to minus 2Vs by 3. From 300 to 360, it is equal to minus Vs by 3. That continues. Therefore, this is the shape of the voltage, of the phase voltage. And the question is that what is the RMS value of this one? To find out the RMS value, so root mean square value. Root of, here each stage you can say that one V root mean square value. Here it is marked as VD actually. It is equal to VD by 3 whole square plus 2VD by 3 whole square plus again VD by 3 whole square plus, of course, this is equal to minus VD by 3 whole square, and here minus 2VD by 3 whole square, then plus minus VD by 3 whole square. That is mean square actually. Square is taken and that take mean is taken, because each one there are 6 stages are there, 0 to like 60 degree, or it is equal to pi by 3 to pi by 3, like that one. Can take that one. Therefore, out of the 6 intervals are there. Divide by 1 by, so root mean square and mean, so square then mean and under square root. So root mean square value is calculated, which is equal to 1 root square root of 1 by 6 4VD square by 9 plus 4VD square by 9 plus 4VD square by 9, or its root of 2VD square by 9. It is equal to root 2 by 3 VD. For root 2 by 3 VD, of course, VD is given as the input voltage is given in a 3-phase 180 is given. DC bus voltage is VD equal to 300 volts. Now substituting the DC bus voltage here, the RMS value of the phase voltage for a 180 degree conduction mode, it is given by root 2 by 3 into VD, or root 2 by 3 into 300, 141.4 volts. Therefore, that is the answer is B. Answer is option B. Same problem here. Another question connected to the same circuit as such, 180 degree conduction mode. In this 3-phase inverter circuit, the load is balanced and the gating scheme is 180 degree conduction. All the switches given are ideal. And if the DC bus voltage equal to 300 volts, the power consumed by the 3-phase load. What is the power consumed by the 3-phase load? And same as we have seen in the last problem. And here plus VD by 3 plus 2VD by 3 plus VD by 3 minus VD by 3 plus 2 minus VD by minus 2VD by 3 minus VD by 3. So that is the one cycle, and we have calculated what is the RMS value of this voltage, which is equal to 141.4 volts. That is and the power consumed is given by, because the per phase voltage is this one. Therefore, the total power equal to 3 times the per phase voltage square divided 3 V5 square divided by R. Or 3 into 141.4 square divided by resistance is given as 20 ohms. Therefore, the resistance, as we are in the previous problem, it is resistance is given previous. That can see that one here. The resistance is given as here. The resistance is 20 ohms. Resistance is given as 20 ohm per phase. Therefore, the per phase power dissipation equal to V phase square divided by R. For total 3-phase, 3 V phase square divided by R, 3 into 141.4 square divided by 20 ohm, which is equal to 2999.09, or approximately 3 kilowatts. For the answer is D is the answer. Answer is option D.